Good afternoon. We're going to start with the binomial distribution today, unless you have any questions from yesterday, the last time we met, about Unit 4, the probability problems, the 4 problems I did at the end. There's a few of you here. Just setting things up. It's taking a little bit to load. I got some virus warning just now. That was very disturbing, but I'm ignoring it. Not sure why it's taking so much time. Okay, looks like we're fine. The assignment's looking good. People are adding a lot of content. Make sure you comment on somebody's post. You have to comment on 3 different posts. And hello, Maria and Caroline. It doesn't have to be long, brief with some substance. I want you to defend your point with other statistics or other evidence with statistics in it. So I really want you to use statistics, not opinion. And what I'm going to do on Thursday is ask a second question or pose a second part to the problem. So I do want you to engross yourself in the comments of other people. And I did say a minimum of 3 comments. So you can obviously do more than that, and hopefully you're going to learn something. I imagine most people are reading, consuming lots of the news. So this is your opportunity just to put some of that effort to use. And we're all going to learn something. Okay, so here we are. This is Unit 5. Unit 5 is in 2 parts. The first part is binomial distribution. So now I go more in depth with the binomial after Unit 4, where we discussed how you identify a setting that is a binomial setting, and then you can define a binomial random variable. And now we're going to use the structure of the binomial random variable to help us answer questions of what to expect in a scenario that a random event is binomially distributed. All right, so recapping here what was discussed in Unit 4, we say that a random variable x is distributed binomial with parameters n and p, provided the following. The random variable x has the possible outcomes that you can list, starting at 0 all the way to n, where n, the small n, represents like the sample size. This is saying that the sample space then will consist of all the possibilities 0 through n. Defining x as the number of successes, it's a count variable, observed in n independent trials. Okay, this is binomially distributed, provided that, first, each time you observe, you are looking for you're looking for a success, and the only other possible outcome is what we call a failure. Number 2, that you actually know the probability of seeing what you're looking for, the success. And criteria 3 is that you know how many times you're going to look in advance. So you know n, in other words. You know small n, you know it, so it's a finite number. It's not an infinite number, and it's fixed or known in advance. Okay, so then I provide 2 examples. Example 1. So if you look at a randomly selected group of people and you observe them to determine whether they're divorced or not. So the divorce would be a success. So provided you knew the probability of success, you could actually estimate out of a certain number n of individual pairs or individual people, how many or what's the chance that they're actually divorced. And number two, let's say on an assembly line you looked at different light bulbs to determine if they're defective or not. In this case, the terminology still remains that what you're looking for is success, but in this scenario, the success is defined as a defective bulb. So just to take a takeaway from that is that success doesn't imply a good thing, it simply defines the event that you're looking for. And secondly, since all we need to know are these two parameters, the two sets of information and the number of attempts to look for the success and probability P of the success, those are all you need to know to define the variable. We'll refer to them as parameters. As a result, they're the characteristics of the distribution that will help us determine answers to questions about probable outcomes. So here are the possible outcomes. I've put them in a distribution. I don't know why my formulas are blurry, but okay. I've placed them, oh, this is messy. I'm not sure. Oh, maybe because I have to make it a PDF. Okay, give me a second. I'm going to make this a PDF. Hold on. Okay, it's just a large file. It takes a while to open, to upload. So, yeah, I'm just going to make it a PDF or it's going to be very confusing. There we go. So, no comments from you guys? How did your review of Unit 4 go? I should have been ready with all this, but I thought I was. Okay, let's go back. There you go. Better. Okay, so now let's look at the probability distribution for a variable that is recognized as binomial. So here it is. This is it here. So what does it say? Here are the possible outcomes. X can be no successes out of n trials, 1 success out of n trials, all the way to n successes out of n trials. So if it's 100 times you try, then that's going to be 100. All right, then this is the probability. Probability X equals K. I use the symbol K because it's going to change, right? So I could put a little x in there, which I usually do, but I'm going to introduce the idea of the k for pedagogical purposes, to explain things in a way that you might be likely to remember, more likely to remember. All right, so these are the formulas for each of the possible outcomes. So this is just, if I have n and p, I can compute this in each case. So what's the difference? What's the pattern? There is a pattern here. And we're going to talk about where the pattern comes from, so you don't have to memorize a formula. Anyway, you won't have to memorize a formula because I will give you this formula. Well, you'll get to use all the formulas, right? But you need to, the best way to work on in this course is to understand the formulas. So I'm going to explain the formula, help you understand it so that you can apply it easily. So, if you notice, as we go with more successes, what happens is P here, the probability of success increases. So the exponent for the probability of success increases. That makes sense. There's none here, there's 1 here, and there's n here. And then what's this? If this is the probability of success, then 1 minus p, the only other possible outcome, is a failure. That's the probability of the failure, 1 minus p. So it's raised to n in this case, because if you have 0 successes, then all of the tries must be failures. All right, so that's why it's raised to n. I'm going to explain this a little more. I'm going to break it down even more in a second, or in a minute. So then here, as you go to 1 success, the probability of success has a power 1, and the probability of a failure has 1 less. So the p keeps on going up, the exponent to p goes up, while the exponent to 1 minus p goes down. So this is the other extreme over here. Okay? So when something is to the power 0, that's just going to be a 1, and this will be successes to the power n. All right, now what's this in front? And why is the formula like this? So this is what we're going to discuss next. Just to summarize, though, this piece, this is the formula for any one of those. It's the same formula. It changes depending to how many successes this number is, okay? So how many successes you're interested in calculating the probability of or for. Okay, so we talked about many cases. Think about the case where we're trying to determine if someone had a telepathy or extrasensory perception, ESP. And in that case, we wanted to know if if the person guessed more than 50 cards correctly by just guessing at the images on a card without seeing the image, then we would have to calculate. We'd have to use this distribution and derive all of the different probabilities for probability that x was equal to 51, x is equal to 52, all the way up to x equals 100. In that case, it was 100. Anyway, so we're going to talk about that example. We talked about the umbrella example. So basically, this is the distribution that we need to derive or elements of it to actually calculate probabilities of certain outcomes occurring. All right, so let's go back to our example so I can derive the formula, and then we'll go from there. So the classic example, and the one that, the one that we used was this one, flipping 4 coins. These are the possible ways. You can see 4 flips of a coin turn out. All 4 coins have a head. In this case, these are ways of seeing one tail and the rest heads. So these are all the possible arrangements. This is for two tails and then 2 heads, all the possible arrangements, and so on. So the way I'm deriving it here, this is showing the probability distribution. It's demonstrating what I want to find. I want to find this one. It would be the probability of this outcome would be the probability that x equals 0. The probability of these happening would be the probability that x equals 1. This would be x equals 2. This is x equals 3, and this is x equals 4. And we already know the answer. We already figured this out. Remember this was going to be 1/4. No, sorry. What am I saying? 1/16, right? Because there were 16 possibilities when you count them up. There's 16 possibilities. They're all equally likely individual events, but as compound events, they differ. So one tail is 4/16. 2 tails is 6/16. 3 tails is 4/16. So if you remember, we discussed this before, and that's 1/16, and they total, all the possible outcomes total, 16/16 or 1. So I know that already. I don't want the answer. I want to derive the formula. So let's take a moment to derive the formula. Let's just take one of these outcomes. One of these outcomes. Oh, that didn't work. There we go. So let's take one of these outcomes. Let's look here. So this is the outcome that I refer to as the probability of a tail and a tail and a head and a head. That's what we're looking at. So let's go the next step. Well, let's break that down. What is that? That's the probability of a tail times the probability of a tail times the probability of a head times the probability of a head. But why? How did I do that? Well, that's because of the rule number 5, right? Probability rule number 5. This is independence. These are independent events. That's how they're defined. The trials are independent. It means that the p stays the same throughout the throughout your observation, the n observations. So I could proceed and just calculate that, but I want to go further. I want to, from this example, I want to derive the formula. So what is the formula? What is the formula for this? If rather than putting the number in, let's put the symbol. So the tail is what I'm looking for. So that will be my success. So I'm going to put a P here. So this one's a little p. This one is also a little p, but this one is represented by 1 minus p, as well as this one is represented by 1 minus p. So these two are p squared, and these two are 1 minus p squared. So that's where that comes from in the formula. So what is remaining? What's remaining is that value in front. So that we've done this so far. We figured out that it has to be P1 minus P, and depending on how many successes you're interested in, the K represents the number of successes you're interested in, and the N minus K is the number of failures. So let's go back to that. So that's what's happening here. It was 2 successes. So then if there's 2 successes and there's 4 total tries, that means there's 2 failures. So let's put the symbols on for that. So this 2 should really be K, and this 2 should really be failures, N minus K. Notice, of course, that K plus N minus K totals N, right? The total number of tries. So I'm splitting them between failures and successes. Sorry, failures, successes, and failures. Okay, and I'll leave that out. So I pretty much derived the first part of the formula, but what is that front part? The front piece is not a fraction, it's actually a matrix. So not a matrix, or a fraction, sorry, it's a factorial. If you remember the symbols from high school, it indicates, well, in this case, 4 choose 2 is 4 factorial divided by 2 factorial divided by 4 minus 2 factorial. I don't expect you to use this, okay? I expect you to compute this with your calculator. I can show you how to do that on your calculator, which is the most important thing. Let me get that. All right, let's see if I can. I have to turn this one off. Wait. Got to. I have to turn this one. Oh, it didn't work yet. Sorry. So I need to stop this. I need to stop this. And turn on my phone. Oh my goodness, this is taking forever. Let's see why I can't do this. Okay, let me stop mirroring. I'm going to stop mirroring this. I can only mirror one thing at a time because I don't really know what I'm doing. And now it'll work. Uh-oh. It's choking. Come on, come on. I'm trying to set up my calculator to show you this calculation. Nope, that's not what I want. Oh, it's not connecting. Why isn't it connecting? What am I missing? Bluetooth? Bluetooth, maybe? I don't even know if it's working on. Let's see, maybe it'll work on Bluetooth. No, it won't seem to give me. It was working before, but now, why not now? Okay, let me. Not sure what, not sure. There. All right. There. Okay, I got it. Hope this lasts for a bit. Okay, so let's see. Here's the phone. Okay, so what you have to find, so I'm going to use my the TI BA2 Plus, but similar symbols will be on any phone that I've asked you to, all right, I said you could use. So you have to go down to the right side on this phone. Oh, wait, how am I going to make sure that this shows, right? I have to make it smaller. I have to make this smaller, right, to fit it. I didn't think I needed to do this yet, sorry. Let's see. Not sure what this is for. I'll have to keep it small. Okay. Well, hopefully you can see that. So what I'm going to do is use the NCR down here with second function. I activate NCR. I have to put a number first. I have to put the N first. The N was 4 flips. 4, second function, NCR, and then put 2, 2, and equals, and that should give me 6, which it does. Did you see that? So that's how that works. So I'm going to use that. I'm going to ask you to use that. Can you guys have a look at your calculators and see? So you should be able to take 4, second function, NCR, 2 equals gives you 6. What does it mean then? First make the calculation, then we'll discuss it. One more time. 4, second function, NCR, 2 equals 6. Okay, I'm going to go back to my iPad. So this means NCR is N choose, C for choose, 2. So it's the number of ways of seeing our successes out of n possible successes. That's all it is. There's actually a symbol for that. It's actually programmed on your calculator. So what's programmed in your calculator is this. Okay, so it knows how to deal with factorials. Factorials would be 4, 3, 2, 1. That's what 4 with an exclamation mark means. It says multiply 4 by 3 times 2. And it's these are combinatorics. These are formula that are useful for understanding arrangements and arrangements, possible outcomes, considering arrangements. So very important for probability and probability formulas and probability distributions and for calculations. So you don't have to do all this. All you have to do is tell the calculator, I want to know how many ways there are of seeing 2 possible for second function, usually NCR 2 equals. That will give you the answer for the TI BA2 plus. Okay, make sure you can get it. Let me know you got it. And that's what goes in front of here, because what you have to do is multiply the probability of getting this outcome, which you figured out. You figured out the probability of getting T, T, H, and H, but that's not the formula. The formula is for all of these in this group of two successes, 2 tails in this case. So I need to pre-multiply the probability of this because these are all the same. And this probability is 1/16, which I already knew, but I wanted to derive the formula for how to get that in the general case. The general case where maybe I'm not gonna flip 4 times. Maybe I'm gonna look at 1,000 people, and I want to know how many of those people can I expect to have something I'm looking for, like we talked about on the first page about if I was interested in predicting the number of people who are divorced. If I know the probability of people being divorced and I look at a sample of 1,000, using this formula, I would be able to predict what's the chance that half of, 50% of the total, or otherwise 500 people, were actually divorced individuals. Okay, so that's what it's for. And we wouldn't want, in the case that it was 100 outcomes that we were observing, we wouldn't want to have to list all of the possible arrangements of those outcomes, right? We simply, with this formula, we see a pattern that we can exploit in the general case. So there it is. So in general, I'm going to write oops. I like this erase tool, but I really need practice. Okay. In the general case, we write n choose k. So the number of ways of seeing k successes out of 4, the probability of success to the number of successes. And then the probability of a failure to the power of the number of failures. The total of those exponents must be n for all the possible outcomes. Well, I guess the total trials is better to say it that way, because an outcome could be 0. So there's actually n plus 1 outcomes, but the total that you could have successful, or that would be successes, is n. Okay, so this is the formula. This is the formula that you need to practice with. Now, using that formula, we could have calculated the probabilities for the probability distribution. This is the chance of 0 successes. This is the chance of 1 success. This is the one we just derived for 2 successes. This is for 3, and this is for 4. And you should notice here there is an additional pattern, not just that we're using the same formula and just changing this value every time. We're not just, that's not, because N and P stay the same, but K just keeps changing. There's actually a particular pattern here in this distribution. You should notice that this number is the same as this number is the same as this number, and then you have the one in the middle. So this is actually symmetric. This is actually symmetric. So if I was to draw this, it would be spikes that would be mirrored around the middle, and the middle would be 2, right? This is actually symmetric. Now, are binomial variables always symmetric? In this case, the symmetry occurs because the P is 0.5. That's what makes it symmetric. Okay, because we just end up swapping. This will be 0.5 and this will be 0.5. Then that's what's going to make this the same as this, because the exponents are just flipped from here to here with the 0.5 odd in both. So, and the same thing here. It'll be exactly the same result because I have 0.5 and then the exponents will just be flipped around. Okay, so that's why this ends up being symmetric. But in general, the binomial distribution doesn't have to be symmetric at all. All right. So I go through many explanations here. I repeat myself, in other words. I explain the same thing different ways. Oh, I want to save this as bin. So again, here's the general probability distribution, and here's what I was saying. You see these exponents here just get flipped around. Okay, and you'll notice the same thing if I spread this out more, but it just gets so messy. Let me show you some online distributions. You could Google or use DuckDuckGo, whatever search engine you like to use. I'll use, I think Safari's on this. And I'll show you binomial distributions. Oh, I don't want distribution, I want binomial tables. So what is, before computers, before calculators, tables were derived because of the importance, and you'll find that the binomial distribution is at the foundation of sampling theory. So these were very important. You see here, this is a table that shows the probability of success being P. I should, it's okay. I don't have my tool to point. Anyway, you see at the top, that's the probability of success, and then on the bottom, on the left side, on the margin, are the possible outcomes. So for, in this case, for a P, different P's, you get one column. Is there another page? Let's see. So most textbooks still have tables at the back. That's not what I wanted. most tables do have, sorry, most textbooks do have tables at the back. So you see this table goes all the way to, so what's on this axis are, and the table continues and continues. So basically on the left side, you can change the end. So it gives you all these possibilities. Let's look for the one that we just did. We did P of 0.5. Sorry, the dummies ad is there. How do I close that? I'm in the dummies book. So, and here is the P of 0.5 in that column for n equals, what was our n? 4. You see right in the middle is our distribution. Okay? Let's see if I can get that. Take a picture. I have those, just some tables in on the website for you to see as well. I don't know where my screenshots go, maybe to my photos. Let me just set this up first. Very strange. Okay, so my screenshot should go to my photos. Sorry, I'm here, just looking. Frozen. Anyway, let me forget about that. Let me get out of here. Okay, so you can have a look at that. Obtaining binomial tables, and you can see that it will give you, with n and p, it just gives you the answers. Another way to generate the binomial distribution for any n and p is to use Excel. You can also do this in Excel. I've entered on our course page in Moodle the codes that you would use for that. So usually to enact a function in Excel, you use the equals symbol, and then a drop-down menu will come with all the possible functions you can use. So if you just type bin for binomial in Excel, you will get, you will be able to generate the distribution. Here's an example I have in the notes of a table. Okay, so you can find tables like this. You pick the P and the N, and this generates all the possible outcomes for you. And notice with a P of 0.25 and an N of 15, it's not symmetric. Oh, this is a cumulative distribution. They're actually adding as you go, so it's not as easy to see. So I'll show you tomorrow. I'll get some tables to just demonstrate what the heck I'm talking about. Right, here are the codes for Excel. You would tell Excel that you want to generate the probability distribution for a binomial distribution. You would mention the K, the number of successes that you would actually want, like if you want the value for no successes, 1 success, 2, or whatever. So I refer to the K as a special K, like the Kellogg's K. which I hope not stealing trademark, but basically to remember that's what the K is. It's the one that you're interested in, the number of successes you're trying to estimate its probability of occurring. N is the total number of trials, and P is the probability of success on one trial. Okay. So, whereas P is the probability of success on one trial, by generating the distribution, you're calculating what's the probability of success overall from all the trials, the probability of getting none, seeing no successes, seeing one success, seeing two success. That's what the binomial generates. So this is what you would put, and you would tell it that you don't want it cumulative. That way it'll just give you it'll just generate the distribution without adding all the elements together. And so that's how you do that. So why am I telling you that? I'm telling you that so you can solve all the problems that I'm going to give you. You can use your calculator, you can use Excel, you can use a table you find online. You can do whatever you like, because that is up to you. So practice and see what it is that you like. So I'm going to show you how to solve some problems. Here is the one I mentioned. Okay, so this is, I refer to as example 2. So this is the one that I mentioned, the ESP example. Well, what's the chance that somebody has ESP? Defining the ESP as someone guessing at least 50 cards correctly. At least 50 cards correctly means that we would have to calculate the probability of X being greater than or equal to 50. Now, that's not the first question I ask. I just want to see, using this setup, the binomial setup, what's the chance of guessing 2 correctly? That's the first thing I want to ask you. So so let's just get familiar with the mechanics of the binomial distribution, and let's calculate the probability that X is equal to 2 using this formula. So actually not 2, it says at most 2. So at most 2, where the possible outcomes are 0, 1, 2 up to 100, at most 2 would be just these ones here. 0, 1, and 2. Okay, so that's what you would be calculating. Oops. So what does that mean? It means I have to apply the formula out of 100 tries, what's the chance of getting none correct times the probability of getting having a correct guess, where P was 1/4. So remembering our elements, P was 1/4, or 25%, and N was 100 tries. Okay, so let's recap. That's the binomial distribution with P equals 0.25 and N equals 100. So I want to calculate the probability that there's no correct guesses, 1 correct guess, or 2 correct guesses. So I give this exercise so you can practice with your calculator and understand what you get on the face of the calculator. So when you punch this in, remember this is 100 NCR 0. So you're going to hit 100 second function NCR 0 equals, and you're going to get the answer there. Anything choose 0 will always be 1. Okay? Why? Anything choose 0 will always be 1. So no successes out of, doesn't matter how many options. Why is that? That's because, let's go back here. Let's go back here. Here's something to notice. The binomial, we call this component the binomial coefficient. Let's say their n is 6. Okay, just like that example that we did. Well, anyway, let's work with n equals 6. I think I just used that as an example. So n equals 6. So what does this mean? This means the chance, or the number of ways you can see no successes in 6 tries. So what is that? Here's 6 tries, 2, 3, 4, 5, 6. And if you have no successes, it means that all the outcomes were failures. So in this try, you got a failure. In this one, you had a failure. This one, you had a failure. This one, you had a failure. And this one, you had a failure. Well, how many ways are there of rearranging the F's to see 0 successes? This is there's just one way, right? That's why all of any n choose 0 is always 1. Similarly, n choose n will always be 1. What does this say? This says, how many ways are there of seeing 6 successes out of 6 trials? Well, let's do that. 6 tries. 1, 2, 3, 4, 5, 6. 6 successes. 1, 2, 3, 4, 5, 6. So how many ways are there of rearranging the S's to get different outcomes? How many different possibilities are there? Well, there's only one. There's only one way to see the S's. Yeah, even if I move them around, they still look like S's. So there's 6. This is 6 successes out of 6. It's also 1. So there's symmetry in the coefficient. These are 1. So the conclusion is, it will always be the case that n choose 0 and n choose n will always be 1, no matter what the n is. Next step is, what about 6 choose 1 and 6 choose 5? Those are the same answer too. Well, how can we remember that? Well, do the same thing. Let's say there's 6 spots. 1, 2, 3, 4, 5, 6 possible outcomes. 6 possible outcomes. 1 success. So here's one way of seeing that. Sorry, one success. So 1 success and the rest are failures. How many ways are there of seeing 1 success out of 6 tries? 1 success out of 6 tries. Well, I could write it like that. I could write it like that, and so on, right? I can make it so you see, by cycling through the success, I'm freezing up. By cycling through the success, you can see that you're going to be able to move, oops, my goodness. You're going to be able to move S through 6 different cycle through 6 different positions in the outcomes. So there's just going to be 6. I could keep going. And there's going to be, in the end, 6 different ways to see that. So that's why n choose 1 will always be n, and symmetrically so 6 choose 1 will always be 6, but symmetrically 6 choose 5 will also be 6. Again, why? Because in that case it will be 5 successes but 1 failure, so you'd have an F being rearranged through the 6 spots. So these are the same, or n choose 0 and n choose n are always 1. N choose 1 and n choose n minus 1 will always be n, and the others will be symmetric. So the binomial coefficient will be symmetric as you move in, but the other part of the formula won't necessarily create symmetry. That will only be the case when n equals 0.5, and in one more specific case, which I'll discuss next time we meet. Okay. So looking at this problem, I want you to try and plug these in, rationalize these results for yourself, and realize we can derive, using our calculator, 100 second function NCR 0 times 0.25 to the 0 times 0.75 to 100. This is going to give you this number. On most calculators, that's what it will look like. What does this mean? This is 3.21 times 10 to the negative 13. It means that you have to put 13 decimal places in front of 10. So it really will have 11 zeros in front of 1 as a decimal being multiplied by this. So it's a small number, that's the point. Anything smaller than 0.0001 I will refer to as 0. Okay, so 0.0001 or smaller will be considered 0. So this, as soon as I see this negative 13, I know this is 0. Okay, so what does that mean? It means that the chance, if someone's just guessing, out of 100 tries, the chance that they'll get no correct guesses is absolutely unlikely. It's probably 0 chance. Okay, 0%. They're going to get some right, but just by chance, they're going to get some of them right. What's the chance of them getting 1 right? Well, it's higher. It's a little bit higher than this one, but it's still 0, okay, because we have that negative 13 power. So that's going to be 0. And then the chance of getting 2 right is still a little bit higher, but it's still going to be 0, okay? So you're going to have lots of zeros in this distribution, but I just wanted to know what's the chance of getting at most 2. And it's unlikely. What would you do with these numbers? You're just going to be adding to get the final answer. You have to add probability x equals 0 plus x equals 1 plus x equals 2, and you find out that that's 0. So it's very unlikely, somebody just guessing will probably get more than 2 right. And what's the probability of getting 12 cards right? Oh, that's my second question. I lost the 2 there. What's the probability of getting 20 cards right? This is part 2. Well, that would just be just to get an answer. So you could write it as probability of getting 20 correct using the formula. This is the chance of getting a correct guess is 0.25 to the power of 20 successful guesses. And then if there's 20 successes, then that means there's 80 failures. So how this works, these always add up to n, in this case equals 100, and these will always add up to 1, okay, because one is a success, the probability of success, and the other one is the probability of failure. So without using the formula literally, I know that this is 0.25, and this is the complement, this is 0.75. This is the probability of success, this is the probability of failure, and this is the number of ways of seeing 20 successes out of 100. If you plug this into your calculator and you keep multiplying straight across, you'll get this answer. Let me show you that, and then we're going to go, okay? Maybe I should, I don't know how much time you have before tomorrow, but it would be nice to start those exercises. Maybe I'll do one before I go. So I want to calculate this. With the calculator, turn this off. Oh, now my calculator isn't working. Okay, let me just say, let me just tell you how to punch it in, right? So this is 100. So you're going to type 100, second function, NCR 20 equals, and then you're going to multiply by you should be able to just multiply. Well, actually, I think this calculator doesn't have order of operations in it. The TI-30XA does, but okay. So then maybe you have to put brackets and then 0.25 y to the x 20 close bracket times bracket 0.75 y to the x. Let me make that a little cleaner. Times 0.75 y to the x, 80. So that's what gives it the exponent, close bracket, equals. That should give you that answer. So practice that. Maybe that's enough work for you. Practice that. Make sure you get that answer. And then we will try the bin problems. So the bin problems are in the homework. The homework that I give you on Moodle also has a folder, or sorry, a document in the bin problems with the solutions to all the homework problems. So you have the solutions for the homework. Okay, the homework exercises. And then there's also, in this notes, there's a bunch of exercises here. Okay, so you can have the answers there. So you can start working through those, and I will do some of them tomorrow. I'm not going to spend the whole class. Well, maybe I will, because it's only an hour. So I will do that, and then on Wednesday, I'm going to start this discussion that leads us into the second part of the unit. All right, so work on the homework for bin, review this video, and we'll see you tomorrow. Bye, good night. I'm seeing Maylin, I didn't end yet. Maylin wrote me 0.74 times x is 0.74 second x. So give it a shot. I don't know why she's saying 0.74. Okay. Bye, Maylin.